I'm currently building up my own 8-bit Superscalar out-of-order processor, and it can already run some simple programs. And so the way we wrote these programs until now is we basically created a new text file and then started typing down a human-readable representation of the program with explicit instruction names like load immediate or move or jump relative, and then the different registers and immediates that go into these instructions. And then we pulled up our instruction descriptions that we had in our isa.txt file, which basically lists how each instruction translates to the bit patterns in hardware. And we went in and manually translated all our human-readable instructions to these hexadecimal and binary representations. And then we would pull up this hexadecimal representation of the program memory and just manually type in these bytes into this hexadecimal representation. And then from that we could generate the binary file that we could flash into the program memory. So there's 4 or 5 steps involved here that are pretty cumbersome and error prone, and I'd really like to improve on this. So that's the goal for today. Let's write an assembler program, a program that can ingest this human-readable format of the instructions and does all the heavy lifting for us and basically spits out a binary that we can flash into the program memory and then have our processor executed. So let's get started by creating a basic input file that we want our assembler to be able to process. And let's use this program that we already have here in this isa.txt file. That was the thing that was running last time that tried our 16-bit absolute chumps. Let me create a test file and let's call it test.s. The .s suffix is a customary indicator that this is an assembly text. So I think we want the format roughly like this, where we can have some indication of where specific blocks of instructions should be located in memory, and then we have the instructions slightly indented listed there. And this is a very common format for representing assembly. And I think we want to have a org directive to basically indicate the organization of the instructions in the final binary. And all it does is it takes a number, which is the address at which the following instructions should be placed at. And one of the important pieces of an assembler is it should support comments in the input, such that we can actually describe a bit more clearly what we're trying to do with the program. And the assembler should just basically skip over the comments and ignore them. So comments should basically work at the end of a line or all on their own. We might also want some multi-line comments. These can be very useful if you quickly want to comment out a block of code. And so we definitely want to support that. Let's change things around a bit. We also want to support different formats for integers, like +18 instead of hex 12. Maybe also want to add comments to show where we intend to jump. Okay, so I think this is roughly the input format that we want to support for our assembler. And what we want the assembler to do is go through the file top to bottom, parse the instructions, try to make sense of everything, compute the exact addresses of each, compute what the encoding is going to be, and then spitting out a binary file that we can flash into the memory. And for simplicity's sake, let's do this in Python again. We make it executable. And we can run the assembler and nothing happens basically, which is okay because the script is empty. So let's change that. Let's first parse some command line arguments, like the list of the files that we would like to assemble. We're going to use the argparse Python library for this. This is pretty handy and there's a good straightforward command line parser. And so this add argument function here basically adds an inputs command line argument, and metavar just changes some of the display in the help page. And args equals star indicates that we can take anywhere from 0 to multiple of these input arguments, and the help text is just what's going to show up in the help page. And then we'll simply parse the command line arguments. Let's see if this works. Alright, so just calling the assembler with no arguments does nothing. But now we have a -h option, which is predefined by the argument parser, and it basically gives you a help page on how to use the assembler. So let's actually take a look at what we pass in as inputs. So if we don't pass anything to the assembler script, we have an empty list of inputs, but we can add our test program, and that's now part of our inputs. And we can add even more, and they all show up in sequence in this list. So this is the one we want to make work. Assembler, and then we pass the test.s program. Let's see how we can do that. I think the first thing we want to do is basically create an assembly parser class and then create an instance of this class and basically go through all the input files and parse each of them into this parser class. So we create an assembly parser instance. We iterate over all the input files we were given and we parse each in turn. Now this won't work now because we haven't defined what assembly parser is yet, so let's do that next. Alright, so this is the function we want to write, parse file, which parses the entire assembly file and stores it somewhere in this parser. So basically what we want to do is open this file for reading, and then read the entire file input, store it somewhere in the parser as kind of the current file we're parsing, and then interpret the file body as a program. And so what we're doing here is we're opening the input file for reading. Then we're reading the entire file into this current input variable that we're storing in the parser. And this basically holds the current file that we're parsing, or the current text that we still need to parse. Then we call parse program, which is a function that we're going to write, which is going to interpret the entire current input as a program. It's basically going through it and parsing the instructions that are in there. And then we are cleaning up after ourselves again. All right, and then so at this point, we should be able to look at the current input variable of the parser, and it should basically contain the entire body of the input file that we want to parse. Let's quickly check if that works. All right, that seems to be working. It basically emits the entire body of the file. Okay, so how do we do the parsing of the actual program? Now the interesting thing is that the program starts with some whitespace and some comments, basically stuff that we don't even want to think about and that aren't relevant for the parser. And so what we want to do is basically skip all of this gunk at the beginning of the file and start parsing here at this first LDI instruction. So let's do that. I think we want a skip function on this parser which looks at the current input and strips away all the whitespace and the comments at the beginning of it, such that the start of the current input variable is basically an actual thing that we're interested in. It's like the LDI instruction, but none of the comments. An easy way to do this parsing is to use regular expressions that match a certain specific string or set of strings. And we can use this here to, for example, skip over whitespace. And so what this does is it tries to match the regex \s plus, which is basically saying gobble up all whitespace in a sequence, and it's matching it against the current input. So basically all the whitespace at the beginning of current input is going to be matched. And then if this actually matches, if there is whitespace at the beginning of current input, this m variable is going to be set to an object which contains information about what has been matched. And then we can actually look at what exact whitespace that we matched, and we can print it out. And so as you can see in the terminal, we actually found some whitespace at the beginning of the file, and it's in fact 4 space characters. And if we go back and look at our test input, there's indeed 4 space characters at the beginning. So that seems to be working. So to skip over this whitespace, we basically want to remove it from the current input. And so what we're doing is we're setting the current input to the current input, but starting after the whitespaces that we have matched. And now the next thing we have, let's actually add a different comment here. The next thing in here is a single line comment. And basically what we want to do, whenever we see such a hashtag, we basically just want to ignore the rest of the line and just discard it as a comment. And so we can again use a regular expression for that. So we match on the hashtag character, but I think we also want to support the C-style double / version of this comment. Then we're going to accept any remaining characters on this line up until a new line or the end of the input. Let's see if that works. If we go back to our test input, the first line here indicates the 4 whitespaces that were parsed. And then we're actually detecting a single line comment, including the new line. This is why the closing angular bracket here is on the next line. So this is basically this part plus the new line. So let's try to parse the multi-line comments. and what we want to parse is a / followed by a star, which we need to escape because it's a magic character in regex land, followed by any characters up until a star and a / again. And we need this $s modifier here at the beginning to make this dot star operator here in the middle match across multiple lines. Because if you look at our input, our / star comment spans across multiple inputs. By default in regexes, the dot operator will not gobble up new lines and will not span across multiple lines. But this $s changes that and makes it look across multiple lines. Let's see if that works. Doesn't seem to recognize the multi-line comment after the single line comment. And the reason for that is actually this whitespace here. If you look at our code, we're basically just checking if we can find some whitespace, then we skip that. If we can find a comment, then we skip that single line comment. And if we can find a multi-line comment, then we skip that. But we don't cater to the fact that whitespaces and the comments can be interleaved and there can be many different combinations of whitespace. And so I think what we want to do is just put everything in here into a loop such that we can just keep gobbling up white spaces and comments until we actually find something that is something we want to parse. So we're doing everything in a while true loop now, and basically whenever we find some white space, we just gobble it up and then we continue the loop. We just start from the top. And then at the very end, if none of these have matched and none of these continues have fired, we're going to break out of the loop because we've hit something that is not a white space and also none of the comments that we support. Let's see if that works. Yeah, it does. That's pretty cool. So let's compare against the input file. So that's the whitespace and single line comment that we already had, that's here. But then afterwards it's detecting another whitespace, which is the indentation here. Then the multi-line comment, which is this whole thing here in one go. Then it finds a lot of whitespace, which is basically all of this here. And another comment, the clear registers to 0 comment. And then it finds some more whitespace, which is everything leading up to the LDI instruction. At this point, if we look at the current input, we should actually be seeing this LDI instruction. Let's see if that works. I'll just print the first 30 characters of the input after the skipping. And yeah, as you can see, the next 30 characters of the input is the LDI instruction plus, whatever then comes afterwards. So that seems to have worked. Let me get rid of these prints. I think convinced myself that the whitespace and comment skipping works. Let me also add some comments. I have a feeling that matching a regular expression and then if the regular expression matches, basically returning whatever we matched and advancing the input to after that regular expression, that's going to be a very common thing that we need in this parser. So let's actually put this into a new kind of function that allows us to do this. So this consume regex function here, it takes a regular expression as an argument. It tries to match it against the current input. If that match is successful, and there's actually something there, it will advance the current input to the point beyond that regular expression that we've matched, so that it's no longer in the input. And it will return this match object, the thing we've been investigating for the exact number of characters that we've matched. So let's make use of this now. Okay, that should not have changed functionality. Let's see if that still works. I added a few type annotations here. We need a package for that. Let's try again. And there you go. So our parse program skips over the whitespace and then basically prints whatever is currently at the input position. And that's the load immediate instruction. And so at this point in our program, what we want to do is basically just keep parsing instruction in the input until we run out of input. So basically, as long as we have any current input left, call the parse instruction function. And so in this parse instruction function, we can basically look at the input and then try to parse the individual instructions that we understand. And so for starters, we have an LDI instruction, which is the first instruction in the input. Let's see if we can parse that. So what this does is it tries to match the LDI instruction, and this \b ensures that there's no additional characters afterwards, that LDI is really the individual word, and then it's going to print just something to the console. And otherwise, we want to emit an error message. So let's see what this does. All right, so here's the current input. This is the print line here. We actually found an LDI instruction. This is basically this part. We've matched the LDI in the input and we skip over it. And so afterwards, this is the next piece of the input. It's basically everything without the LDI in front. And then in the next iteration, we actually hit this case here, the self.error, because we don't know what this is. It doesn't start with an LDI and everything else we don't understand yet. And then it tells us that we haven't defined this error function here, which is something I think we want to do now. It usually pays off to add some good error reporting when you're writing a parser, not just for debugging the parser, because it's going to be easier to interpret what's going wrong, but also for the user to use it. It's going to be a lot more convenient if there's a nice error message there. And so what we're doing is we're just printing the error message to the standard error output of the program, and then we're just exiting. And indeed, that's what happens. We see unknown instruction and the exit code is 1, indicating that an error happened. But it would be kind of cool if we could see what actually went wrong, where in the file we are, and what was the input that actually tripped up the assembler. And I think there's an easy way for us to get that. So I think what we want to do is, before we actually start parsing, we want to remember what the current file is that we're in. And after we read the entire input, we also want to keep track of that input in a separate variable that doesn't change. Because we keep modifying this current input, we keep chopping away things from the beginning. And I think it's going to be good if we also have the unmodified version of the file input somewhere around, because we can make use of this to report an error now. So I think what we want to do is try and figure out what line we are actually on, where the error happened. And so to figure this out, I think first we need to know how many input characters we have already consumed. And this is fairly simple. We just take the length of the original contents and subtract the length of whatever remains to be parsed. And what we're left with is everything we've chopped off in front of the current input, basically everything we have consumed already. And then to figure out how many lines we have consumed, we just check how many new line characters are in this initial portion that we've already consumed. So we're taking the current contents and we're taking the slice from 0, the beginning, all the way up to the number of characters we've consumed. So basically everything that is no longer in current input that we've already gone over. And then we're splitting this up by new lines. And what this gives us is consumed lines as an array, where every line that we've processed is a separate entry in the array. And so the line number is actually pretty easy to figure out. It's just count how many lines are in this consumed lines array. But we can also figure out how many characters into the line the error happened. So how many positions from the beginning of the line to the right the error occurred. This basically takes the last line of these consumed lines, and this only contains the part that we've already read. This doesn't contain everything that we still have to parse, and we're just taking the length of that. And that should give us basically the number of characters up to the point where parsing failed. And we can also figure out what the remaining characters on the current line are, basically whatever's left in current input up to the next new line. We do this by taking the current input, splitting it up in lines, and then just taking the first line. This gives us basically everything up to the first line. And then let's see what each of these actually contains. So this should print how many characters that we've already consumed, what line and column that the error occurred, how much of the current line we have already consumed, and what the remaining line after the error is. Let's see if this gives us any indication. All right, forgot about this detail. We have to convert this to a string. And there we go. So we get consumed equals 111. This basically indicates that there were 111 characters up till this point here, just after the LDI instruction. Let's see if that is correct. So if I make a selection here until the end of LDI, right at the bottom you can almost not read it. It says 111 characters selected. So that seems to be working. Then furthermore, it indicates that the line was 6, so that is correct. We are on line 6, and the column was column 7. So this is column 1, 2, 3, 4, 5, 6, 7. Now most text editors display the column starting at 1 here, but what we're doing is we're counting from 0 at the beginning. So I think what we want to do is we just want to add a 1 there for the output. So now it says column 8. And if I click here and check my editor, the editor also says that this is column 8 on line 6. So this location information is correct. And then the consumed line, this is also correct. This is basically everything from the beginning of the line up until the point where the error happened. So that's LDI consumed. And then the remaining line is essentially everything that's left here. So that seems to be working. And I think we can use this now to create a nice error message with some beautiful colors that makes it easy to see what went wrong. I think we want to use this term color package that we have used before, which has this colored function that allows us to print colored output to the terminal, which is very handy. Let's first write a colored error message to the terminal. Let's maybe say error colon in red and bold, followed by space, and the message in bold, and a new line. Let's see if this works. It sure does. This gives us a nice error message in the terminal. Okay, but now let's create a nicely formatted error indication here as well. I think we first want to show which file and line and column the problem occurred on. All right, so that should print the file, line, and column. And it sure does. Afterwards, let's maybe add a new line. And then I would like to see the actual line of the input where the error occurred being printed. And basically all we have to do is take the consumed line and the remaining line, and together they form the full input line. Let's maybe add some space in front. Let's see if that works. It does, pretty cool. So we get an unknown instruction error. We see the file where the problem occurred, and we actually see the line in the file where the problem occurred. And now it would be cool if we could actually get a pointer to where the issue was, like something that points here and says, here's the issue. And I think that's pretty easy to do. We just create another line. We fill it with spaces up to the point where the problem occurred, so column number of spaces. And then we can add like a caret symbol here that just points upwards. Cool, nice. So as you can see, we actually get a nice pointer to where the error is. It's actually exactly here. So with this, I don't think we need all of the noisy output below that. And this is essentially our error reporting routine. When I run that and the parser trips over something, we get a nice message indicating what the problem was. And so apparently starting here after LDI, there's something that is not an instruction. And obviously it is not an instruction because we don't know how to parse LDI yet. All right, so let's get back to parsing and let's see what actually went wrong here. So we parsed this LDI properly, but then we didn't do anything afterwards. We just returned from parse instruction and pretended that LDI was the full instruction to be parsed. And then the loop up here tried to immediately parse another instruction, which then failed. So I think what we need to do is, if we detect that this is actually an LDI instruction, we should actually parse the register and the immediate operands that it has. So let's try to come up with this parse register function. So this should be fairly easy. We just parse a regular expression again and then try to make sense of what register was in there. And so the regular expression we want to parse here is basically an R followed by any of the valid register indices. So for us, that's the number 0 to 6. Then we want to make sure that there's a word boundary. So if that didn't work, we probably want to complain. So we're parsing the register and getting the basically the match of the regex in this m variable. If the match didn't work, we're throwing an error that we expected the register. And if it worked, we're printing the number that we've matched here. So basically the first parenthesis in the regex we're printing out. And this should print us what register operand we've seen. And let's see if this works. All right, that's pretty interesting. So we find the LDI instruction, and then we try to parse a register, but we actually error out. And if you look closely, this actually makes sense. There is no register here. There's white space here. And the register only follows after that space. And so what we want to do is after we read this LDI, for example, we not only want to remove that LDI from the input, but we also want to gobble up any white space afterwards, such that we're in a position where immediately at that position, there's something interesting to be parsed. And I think this is going to be so common, this skipping over white space after you've parsed something, that we want to add this to this consume regex function that we already have. And I think we want a skip option here that is set to true by default, which basically just calls the skip operation immediately after parsing something. And so if we've parsed something and skip is set, we call the skip function. And now we need to make sure that the parsing we do inside the skip function doesn't try to skip, because otherwise these might call themselves in an infinite loop, which would be bad. And so let's see if this changed anything. Let's see if we now parse the LDI input and then also skip over the white space. And indeed, it worked. We actually get this found LDI instruction print, and then immediately afterwards we get the register number that we've detected printed out, which is this part here. And then afterwards, we're basically back to trying to parse another instruction, because we're not doing anything with the comma yet. We just try to parse this register. And we get another error message basically complaining that this comma is something that we don't know how to deal with. And so let's parse that comma. Basically going to be the same thing again. Let's see if we parse that comma now. We sure do. The error is no longer at the comma. We detected the comma properly. Then we skipped over the white space here. And now we're at this point trying to parse an immediate. And let's try to change this comma in the input to see if this error message actually works. And sure enough, now we see an error message basically saying that we expected a comma, but there's this colon here instead. And so this pattern looks also like it's going to be everywhere in this parser. Try to consume a regular expression, and then if we can't consume it because it isn't there, printing an error message. So let's actually create a helper function for this that helps us deal with this. Let's call it parse regex because it actually requires the regular expression to be present, and if it isn't, it will error out with a nice message. So that should basically do the trick for us. We give a regular expression to this parse regex function and optionally a message. And then it tries to consume this regular expression. If it works, it's going to return that. And otherwise, it will produce an error, either the error message we gave it, or if we don't give it an error message, it's just going to say expected and then whatever the regular expression was. And this should now make parsing the register a bit easier, because we can just use parse regex for this. And also up here, the parsing of the comma. And let's see if this still works. And it sure does. From the LDI instruction, then we see the register number that we've parsed. So next up, after this comma, we want to parse an immediate value, because this is basically the format for the LDI instruction. It's LDI, the destination register, a comma, and then an immediate operand. So let's write the immediate parsing code. And so parsing an immediate is going to be a bit more tricky because there's many different flavors of numbers that we want to support. For example, numbers can have plus and minus prefixes to indicate whether they're negative or not. There can be just regular numbers like 42, or they can have a base prefix like 0x for hexadecimal, or 0O for octal, or 0B for binary. And so let's see what we can do here. I think first of all, we want to parse the optional sign of the number. And so we use consume regex because it's optional. So we only enter this if branch here if we actually found and consumed a sign. And then I think we want to set a negative variable to true in this case. So by default, number is not negative, but if we see a sign, we set the negative flag to true if the sign we've parsed is a minus. And if it's a plus, we just don't do anything. And now let's deal with parsing just regular numbers. So let's say base 10 numbers. The regular expression for base 10 numbers is pretty simple. We're basically just consuming one or more numbers between 0 and 9 in a row. And so all we have to do is actually parse this and then convert it to a Python integer. So this value we have here is basically the regular expression match, and the 0 subscript here is taking the entire match, everything that we've parsed. And base is basically indicating what the number base is. And we're using base 10 now, and this is going to give us a Python integer. And then if we have a negative sign, we also want to make the value negative. All right, and then let's print whatever we have parsed. And as you can see, we actually parsed an immediate. It was the number 0, but it looks like it only parsed the leading 0 here in front of the x indicating the base specifier. And so indeed, we're actually not doing anything to handle 0x or 0b or 0o, the base specifiers. So let's look at how we can handle those. So before we do any of the parsing, let's check if there's this optional base prefix. So basically we're looking for a 0 followed by x, o, or b. And if it was 0x, it's a hexadecimal number, so base 16. And we want the numbers 0 to 9 and the letters A to F in both lower and uppercase to be valid hexadecimal digits. I think here we also want to make sure that this is the end of a word. And then let's keep doing this. This is octal. Base 8 only supports the digits 0 to 7. And this is binary. Base 2, just supporting the digits 0 and 1. All right, and I think that should do it. So by default, we parse base 10 with this digit regular expression, 0 to 9. But then we also check if there's this optional prefix for the base, and we actually adapt the parsing behavior. If we see a 0x, we parse base 16 with more characters. If it's 0o, it's base 8 with just legal characters for base 8. And if it's OB, it's 2. As the base, and we just parse the 1s and 0s that binary digits can have. Let's see if this works. Cool, that seems to have worked. So we found an LDI instruction, we parsed a register, it was a register 0, and we parsed an immediate, and it happened also to be the immediate 0. And then the next instruction after that is a move, because we skipped everything at the end of the LDI. So basically we parsed this, and then this was all skipped as part of Whitespace, and now we're at the move instruction. Let's see if we can type in some different values here and have them show up. Yeah, that looks good. So this 4 corresponds to the register R4 that we typed, and this 171 is the hex AB that we have here. And we should also be able to just type a regular integer. That works. Can be negative. That works. Plus sign is ignored. That works. Let's try octal. That seems to work. And binary. That also seems to work. That is pretty cool. One feature I'd like to have in these number literals is I want to be able to have an underscore in here to just separate out parts of the number. And the underscore should just be ignored because this makes it easy, especially for binary numbers which have a lot of digits, to split them apart a bit and make it easy to read. But right now this probably doesn't parse. Yeah. So it expected a base 2 integer at this point, but the underscores are in the way. And the way we can make this work is we can just allow underscores as part of the digits, which is going to parse them and gobble them up, just like the rest of the number. But then we actually want to make sure that we replace all the underscores just with an empty string so they disappear. And there you go. That worked perfectly. So regardless of how many underscores we have in a number, it still gets parsed properly as a 147 in this case. Restore this back to the original version. Let me get rid of this print here. And also the found LDI is no longer needed. Now let's think about what we actually do after we have the register and the immediate parsed, because we have the information and currently we just throw it away. We're not doing anything with it. But I think we want to actually create an instruction object with the operands, the register and the immediate, in there to kind of capture what the instruction was that we have parsed. And so I think the first part of that is going to be parsing a register and an immediate into an operand object. And so let's see how we can cook something like that up. Let's maybe do this all the way at the top here. And so I think we want an operand class, which has a kind, which is basically indicating whether it's a register or an immediate or any other special operands we might cook up. And then a value, which holds the register index, for example, or if it's an immediate, holds the immediate value. I think we want to make this a data class so it's easier to construct and work with, just some Python idiosyncrasies. And so we need to specify the different operand kinds that we support. And Python has this enum class that we can use for this, which is pretty handy. And what it allows us to do is basically list all the different flavors of operand kinds that we support. So we support an immediate operand and we can assign it a value. Probably it's going to assign a 0 or a 1 by default. And then reg is going to be a register operand and it's going to assign just the next number, probably 2. And so when we have an operand, let's actually define a textual representation of it such that we can easily print it to the console. And Python has this magic repr function here that stands for representation, and it allows you to basically produce a string representation of whatever class you're in. And so for an operand, for example, I think we want to print the operand kind, the name of the operand kind, so immediate or reg, and then the value. All right, so let's make use of this. In our parse register function here, for example, instead of storing the regex match, I think we just want to take the number of the register that we parsed and then convert it into an integer. That's going to be our register index. And then we return a new operand. The operand kind is reg and the value is index. And then similarly for the immediate, we can do kind of the same thing. We return an operand. It's an immediate operand with the value that we've parsed. And so here, after we've gone through all of that, we can basically print what we've found. So we parse an LDI with RD and immediate. And that seems to be working pretty cool. So as you can see, we print LDI, for this print here, and then the first operand was a reg operand, and it was register 0. And the second operand was an immediate operand with the value 0. And if we go back in and type in some arbitrary values here, these will show up for the operands. So that seems to be working. Pretty cool. Now we want to package the two operands we have up into an instruction and also add a note that this is an LDI instruction. And I think we'll do the same thing as we did for the operands. We're going to have an instruction class. It's going to be a data class. And it will have an opcode, which indicates what kind of instruction that it is. And it will have a list of operands. And this part here just indicates that by default we just create an empty operand list if we don't specify one. And so let's specify this opcode now. We're going to do the same thing as we did with the operand kite further up. Going to create an enum again. And for now, let's just add this LDI. So let's go back to our instruction parsing code, and let's actually package this up as a dedicated instruction. So whenever we're done parsing an LDI instruction, we create a new instruction object with the opcode LDI and a list of two operands, RD and the immediate value. And so parse instruction now actually returns the parsed instruction. And when we parse the program, we can actually store the instruction that comes back here and we can print it. Let me add a custom printing for the instruction here, similar to what we did for the operand. Again, custom string representation. And by default, it's just the opcode name. But then we're going to also append the operands. And so this should allow us to print the instruction that we've parsed. And let's see if that works. Yeah, pretty cool. So we're actually now getting an instruction object with its opcode set to LDI and register R0 and the immediate value 0. That's pretty neat. So what's next on the list? We're complaining about a move instruction here, which we don't yet support. And move is pretty simple. It's MV and followed by two register operands. First, we want to add another opcode, MV. And so let's implement the instruction parsing. Alright, so when we see LDI, we parse RD and an immediate value, and when we see MV, we parse two register operands, operand RD and operand RS. Let's see if that works. Nice, beautiful, that seems to be working. So we see the LDI, that's the first instruction here, and then we basically have the move instructions afterwards being parsed properly. That is pretty cool. And now looking at it, I think this consume regular expression just to consume and kind of identifier just a bit of text, and this is going to be common. So we might want to again move this into a dedicated function. All right, so let's keep going. There's a jump relative immediate plus 18. That's the next instruction that we cannot parse. Let's deal with that. So again, we add an opcode for it and the parsing code. This instruction is easy. It just has an immediate that we use for jumping. Let's see if that works. And it sure does. Jump relative with immediate, with an actual immediate. And now the next issue is this .org magic thing that we've added. And the reason why it's here is we probably have other dot directives in the future, like a dot include to include another file, or a dot byte to add a arbitrary byte to the output stream, or a dot word, or a dot fill, where we can fill a region of code with zeros. And so these directives, I think we want to natively support. And the way we can do this, I think we can represent them as just special instructions that we don't really emit to the final binary, but they're just there in the assembly to help us lay out the instructions. And so basically, I think we have a list of actual instructions that we can parse and a list of directives that we can parse. So whenever we see a .org identifier, we just consume this immediate value right after. And then we create a new instruction with a special opcode, and let's call it d_org. So let me add this opcode. Let's see if this works. Yeah, it does. It parses the org directive here properly, and then it continues on to parse the big block of LDI instructions we have here. And then next troublesome instruction is jump relative with register, which is all the way down here. So let's go and parse that one. So we need a jump relative with register opcode. and then we implement the parsing, and it's going to be easy. We just check for jump relative with register. We parse a register instead of the immediate, and we store this as the operand. And as you can see, the jump relative with register also worked, and it has a register operand. Next up, the easiest of them all is the NOP instruction. And so this basically just needs another opcode. That works as well. So after the relative jump here, we have two NOPs, which are here in the input, and now the two LDIs, and then we are at the jump absolute with register down here. Let's see how we can parse that. Now this instruction is special because the source register that we are reading is actually not a regular register, but it is a register pair. It's a 16-bit value, so it's the registers R0 and R1 concatenated into a 16-bit value. So we need a new parsing function for that. So we're parsing a register pair, and then we just package it up into a regular instruction as we used to do. So let's define this parse register pair function. And so the regular expression we want to parse is basically just two registers immediately one after the other. So that's one register, and that's the other register. Okay, and then let's store the parse result. And so when this regular expression matches, we get this match object back, and it has three indices. Index 0 is going to be the full thing that we matched, or 0 or 1 for example. The first subindex is going to be whatever's in the first parentheses in the input, so that's the 0 of the first register. And 2 is going to contain the second parentheses in the input, and that's going to be the 1. So we can use the subscripts 1 and 2 to get the actual registers that we've parsed. And so the lower register is going to be the first one, and then the higher register is going to be the second one. And we also want these as integers. And now we need to make sure that someone doesn't type something like R4, R3, which is the wrong way around, or R4, R0, which is too far apart, or R0, R3, which is too far apart in the other direction. Basically, the invariant that we want to uphold is that the high register is always the low register plus 1. And so if that's not the case, we want to emit an error. And then assuming that all goes well, we can just return a new operand here. I think we want a new operand kind for this, a register pair. And let's just store the low register index there, because the high index is anyway always the lower one plus 1, so we don't need to store that separately. So all we need to do is add this reg pair operand kind. And let's see if this works. It actually works. So all the way up here, there's the jump absolute with register instruction. And as you can see, we parsed a register pair, and it's the register pair with the lower register set to 0. And that's exactly what is here. And what we can do now is we can try register pair 2, 3. And you can see here the register pair is now updated to a 2, which indicates that the register pair starts at value 2. Let's see if we type in the legal combination of registers, R2, R4, and we get an error, indicating that registers in 16-bit register pairs must be consecutive, and we got R2, R4 instead. That's pretty cool. It does point at kind of a weird location because it actually successfully parsed the registers, but that's going to be difficult to fix for now. So let's just deal with it, and let's assume this doesn't happen too often, but we might want to fix this in the future. So let me return this back to its original state. And now if you take a closer look, we actually ran all the way through the rest of the program. I think we have all the instructions that our CPU supports implemented in our assembler. There's the NOP, load, immediate, and move, and the 3 jump instructions. And if we go back to our ISA, there's the NOP, load, immediate, and move, and the 3 jump instructions. And so another thing we can do is we can add a HALT pseudo instruction, which is basically what we've defined here. It's just a relative jump immediate that jumps in place, but it's a cute little thing that we can add. So when we parse instructions, we can have a section for pseudo instructions. And this is going to be very easy to parse. It's just like a NOP. Let's add a halt here into our program. For example, after this jump, which is never reached. And let's see what happens. And yeah, so after the absolute jump, there's a halt instruction. That never really materializes because we jump over it. Alright, so we're actually parsing the entire file now. And so I think the next thing we want to do is, instead of just printing the instruction, we actually want to store the instructions in an array where we have access to them later. So here, once we've parsed the instruction, let's actually store it in a program variable. And maybe let's actually skip printing the instructions. And then let's create this program variable. And so essentially when we create an assembly parser object, it will have a empty program list internally. But then as we call parse file on it, it will slowly start populating this program list and basically just gobble up all the instructions that it can find in these files. And so all the way down here, after we've parsed the input files, we should be able to just print the program. And indeed, this gives us a long list of instructions with all the instructions that we have parsed. That's pretty cool. As a next step, once we have parsed all the instructions into a program, our assembler is going to do some layouting. It's going to figure out at what addresses each instruction needs to be, and it also is going to figure out the encoding of the individual instructions. And so it would be good if we had a way to print the parse program, or print the assembly in general, back out to the terminal such that the user can inspect it. And if it has additional addressing or encoding information, that we have a way to display that. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.